Alrighty, so yeah, I'll do a quick little intro that I'll just ad lib, and then we'll talk about the
Okay.
books. So,
All right.
alrighty, so this is a little special intro to some of our interests, especially. Now I'm going to say our interest. I'll say Alex's interest for Turing rabbit holes. There are some books that are especially influential, so I thought I'd give Alex a chance to present his books and to talk about how they've influenced him and his ideas.
Right. So I'm always interested in the simplest approach to anything and everything. And this book right here on quantum fields is my favorite physics book. And it quickly shows in the first two chapters, in fact, the first three chapters, how the standard model as we understand it today is built together by symmetries. It begins with the Dirac equation, and it's a relativistic equation for the electron. And if you give it a Lorentz transformation, it should come back out as a Dirac equation, and it doesn't. And if you fiddle around with it, you have to add terms to it. And when you finish fiddling around with it, the terms that you've added are Maxwell's equations. So if you want a theory, a relativistic theory of the electron, you must have Maxwell's equations.
Do me a favor, we go ahead and hold that up real quick, and we'll have our lovely camera lady zoom in. That's Angela. Thank you so much, Angela. Cool. When did you discover this book?
Probably 20 years ago.
Oh, okay. Did you get that, Angela? Oh, very good. Okay. And what's but yeah, of course, as you guys know, Angela is our camera lady. Thank you so much, Angela.
So it's Quantum Field Theory by Lewis Ryder.
Cool. Excellent. Very good. Anything else you want to say on that book?
Well, yes, it develops using group theory. The theory of the electron, if you notice in your complex analysis, if you multiply something by e to the I angle, and you multiply it by its complex conjugate, e to the I angle times e to the minus I angle cancels out to 1. So wave functions in quantum mechanics are invariant under transformations of the circle, which has a fancy name, U1.
Okay.
The extension of that to the electroweak theory was to look for a bigger group called the SU2 group, special unitary group 2, and that suddenly has 3 carriers of force, and through symmetry breaking a trick, you can give them mass. And so the extension of Dirac's idea to a higher group explain electroweak physics, and then an extension to a higher group, SU3, that has 8 carriers of force, suddenly was useful for describing the strong nuclear force. So a lot of physicists begin to explore larger groups, SU5. And SU5 has more particles predicted, and it predicts that protons decay. And right now, we're pretty sure that protons don't decay for at least 10 to the 35 years. We basically put protons, called water, in a large tank and wait with sensors. And we go, yeah, because 10 to the 35 years, but eventually something's happened now. And we've detected no decays of protons. So there's a continuous search for larger groups to try to understand physics. What's interesting is the approach that in that yellow book is called gauge field theory. And at the end of it, the physicist Ryder begins to compare that the mathematics starts to look like the mathematics of general relativity. General relativity has symmetries, groups that are geometric. In classical physics, if you say energy is conserved, that means that no matter how long you wait, move time back and forward on a recording, the energy is a constant. Momentum is another constant of classical physics. In general relativity, it has its four-dimensional space-time conserved quantities. Anyways, he begins to see that there's a nice parallel between the formulation of a geometric theory and the formulation of group theories, which brings me to the second book by Nash and Sen.
Okay, let's do a quick little zoom in on that book so we can see it. So all of our readers can go to Amazon and get a copy of both of these wonderful books.
I wouldn't recommend it.
So really, okay, we could then market it this way. We could say, not recommended because of the complexities, but Alex has gone through the derivations, and can explain them to you. How's that?
Right. So it turns out that in parallel, the mathematicians were working on developing something called gauge field theory, fiber bundle theory. Yeah. And fiber bundle theory codifies either geometry-based theories like general relativity or group theoretic theories like the standard model. So it doesn't care. If the group theory is coming from transformations in geometrical spacetime or from internal symmetries, it doesn't care. But it gives the physicists some handcuffs and to not waste time. For instance, there in terms of spheres that have the nice properties to support theories of physics, it would be only three spheres: S1, S3, and S. It's S0, S1, and S3.
Okay.
Are the spheres that have nice mathematical properties.
Nice.
S2 is the two-dimensional sphere, and it has the problem of the hairy ball theorem.
Sorry, every time I hear that word, I laugh. On our Breaking Math podcast, when we had you on, we were talking about the hairy ball theorem. I actually hired a comedian who does impersonations to do Beavis and Butthead. He said hairy ball theorem. He was pretty funny.
Yes.
I can't do it as well. Now, actually, I wanted to interrupt you real quick because for our listeners who are listening to the audio version, not the video version, can you tell them the name and author and publication of that,
Sure,
that
it's
book?
Topology and Geometry for Physicists by authors Nash and Sen.
Okay. And I know you were talking about the hairy ball theorem. You were also talking about the different, I'm sorry, the terminologies, the groups, S0. How many groups are there in total?
There's a large set of Lie groups. The biggest one is E8, which is one of the candidates for theory of everything.
Oh, wow. Okay. Very good. And what you're saying is that through the work of these mathematicians and physicists, they have narrowed down the groups where there is, where we see applicability in the standard model of physics. Not all of them have equal applicability.
So in a sense, if you're playing, I'm going to design a universe today, fiber bundle theory restricts you to what you should bother with and what you shouldn't bother with.
Okay.
For hyperspheres, like anything above the four-dimensional hypersphere S3, there is no need to bother with that kind of looking for that as a theory of physics.
Okay.
Whereas the physicists, they're a little bit more unconstrained. They may not be aware of the restrictions.
Nice.
So
Okay.
it's a very nice tool.
Okay. Wow. Very good. Wow. Man, whew, that was quite a discussion there. There are some terminologies here. I'm sure I'm not the only one who was sitting there, just smiling and nodding while my gears are turning. So yeah, but still, I love hearing about it, and it gives me a whole lot to think about and to consider. I know you've got you've been doing this for a lot longer than I have. So
a lot longer than I should have been doing it, because the way physics is taught, it's not taught in a unified way. I think in medicine, after your basic medical training, you go off and become a cardiologist or an oncologist, and there's definitely specialization, and definitely in physics are experimental lasers and experimental accelerator physicists, but I think all of them, when you get a 4-year degree at the appropriate level or a master's or PhD, there should be a finishing course showing you there's really a very few set of ideas, Lie's differential equations, Noether's theorems, and fiber bundles, that really shows that physics is extremely unified. And what I've done is I've built probably over 1,000 pages of step-by-step notes, that for you to not have to battle these books and not have to spend 20 years to figure it out.
nice. Now, I hate to not recommend a book, but rather we'll say it this way: for those who Alex has taken these books and he's processed it, and he's made some papers that are available. Will they be available on our website? Yes. Excellent. They will be available on our website. So if you'd like to see more of this, and I love this idea of a physics finishing course, as it were, to really help put things into perspective. The analogy I used, the whole forest for the trees things, but like seeing how these big ideas fit together and having discussions and having some level of comprehension that you might not get in your regular physics courses, perhaps. So I'm sure you're not the only one who feels this way, but you've gone out and you've published some papers. I say publish, and as in made them available.
Made them available, yes.
Yeah, so very cool. Well, thank you so much for introducing those two books to all of us and to the papers available. What are the titles of the papers? Do you remember?
They're probably named very similar: geometry, topology, algebraic topology, fiber bundles, combinations thereof.
Okay.
I have them on classical mechanics, quantum mechanics, mathematics, you name it.
Cool. We'll put a bunch of them up there on the website, and we will identify them there. So, all right. Well, thank you for this little mini episode on two of Alex's favorite books. Be sure to watch more of Turing Rabbit Holes on this channel, as well as on this podcast channel. We're on YouTube. We're on Anchor.fm, Google Podcasts, Apple Podcasts, everything. So be sure to subscribe and send us any emails at turingrabbitholes@gmail.com. That's not touring like you're, touring, a city. It's Turing as in Alan Turing, TURING, RABBITHOLES @gmail.com. We look forward to hearing from you.